I want you to do something for me. Close your eyes.
Oh, boy.
No, seriously, humor me for a second. I want you to picture an atom. Just the classic high school textbook version. The one that's permanently burned into your brain from 10th grade chemistry.
I suspect I know exactly what image is forming.
Oh, I bet you do. It's that little solar system, right? You got a nucleus in the middle, probably a cluster of red and blue grapes representing protons and neutrons, and then you have these electrons whizzing around in perfect circles like little
Like
planets.
the Bohr model.
Yeah.
It is the universal icon of the atomic age. I mean, it's on the logo of the Atomic Energy Commission. It's in cartoons. It's literally everywhere.
Right. But then if you took a little more chemistry, maybe, AP Chem or a college course, the teacher came in and said, actually, forget that. That's wrong. And they replaced the solar system with
Balloons.
balloons. Yeah, the orbitals, the dumbbells, the donuts, those weird four-leaf clovers. We call them shells, electron shells. And we are told that electrons live in these shells, like 1s, 2s, 2p.
And that is usually exactly where the explanation stops.
Exactly. And that is the thing that has always bugged me. It's like a splinter in my mind. We are taught these shells as a set of arbitrary rules. Okay, class, memorize this. The first shell holds 2 electrons. The second shell holds 8. The third shell, well, it gets complicated. It feels like memorizing zip codes.
It feels like geography.
Yes.
You are memorizing the map, but no one is telling you about plate tectonics.
Yeah.
You are given the shape, the number of slots, but rarely the deep why.
Why shells? Why not just a chaotic swarm? Why not a cloud? Why does nature insist, at the fundamental level of reality, mind you, on organizing itself into these discrete, layered onions? Why is the universe an onion?
That is the question of the day.
And today, we are going deeper into that question than I think we ever have. We are doing a deep dive into a set of source materials that honestly blew my mind. We're covering a paper called Spherical Harmonic Review and a very dense, very fascinating work titled Symmetry and Spectral Closure in Shell Structure Formation by Philip Lillian.
And Lillian's thesis is radical.
It really is. The claim here is that these shells, the shapes we all memorized, aren't accidental. They aren't just artifacts of the specific force holding the atom together. They are inevitable.
Precisely. The argument is that if you have rotation, just the raw concept of rotation, and you have a system that closes on itself, you must have shells. It doesn't matter if it's an atom, a nucleus, or a planet. The shells are a structural consequence of the math of symmetry.
You called it ontological physics before we started recording.
I did, yeah.
And I made a face, because ontological physics sounds like something you say to get kicked out of a party.
I stand by it.
I know you do.
Ontology is the study of being, of what actually exists. Lillian is arguing that we need to stop looking at orbitals as just shapes we calculate to match experiments. We need to see them as fundamental consequences of how reality is structured by symmetry. He actually organizes this into a 4-layer ontology.
A 4-layer ontology? That sounds like a bean dip.
A very intellectual dip.
Right. Well, we are going to unpack those 4 layers. And I promise you, we are going to take our time with this because the payoff is huge. We are going to demystify spherical harmonics, which sounds like a prog rock band, but is actually the key to everything. We're going to look at the magic numbers of degeneracy. Like, why is it always 1, 3, 5, 7?
And we're going to talk about a concept called the activation criterion, which is basically the universe's rule book for when a shell is allowed to turn on.
But I want to start with that feeling of ontology, because when I read this paper, I felt like I was moving from memorizing the periodic table to understanding the actual engine that builds it.
That is the perfect way to frame it. We're going to look at the engine.
So let's jump into section 1, the relational layer. And we really have to start with the object itself, spherical harmonics.
The fundamental building blocks of angular theory.
Okay, stop right there. Spherical harmonics. I hear that, and my eyes glaze over. I think most people's do. We think of those diagrams in the textbook, the sphere, the dumbbell. We think, oh, a spherical harmonic is just the shape of the electron.
That is the common intuition. But the source material, specifically Lillian's framework, argues that this is ontologically backward.
Backward? How can a shape be backward?
Because you are thinking of the shape as a thing, a physical object floating in space.
Like a balloon.
But according to the 4-layer ontology, that shape is the result of a process. It's the end of the line, not the start.
Okay, walk me through the layers. If the shape is the end, what is the very beginning?
Layer 1 is what Lillian calls omnilectic invariance.
Whoa, pause. Omnilectic invariance. I feel like I need a PhD just to pronounce that. Break that down for me before we move an inch.
It does sound intimidating. But let's strip away the Greek. Omni means all, or universal. Lectic comes from gathering or choosing, think dialectic. But in this physics context, he's talking about a rule that exists before anything material exists.
A rule before matter.
Exactly. Think of the concept of rotation. Imagine a universe with absolutely nothing in it. No atoms, no light, no empty space even, just pure math. Does the concept of a circle still exist?
I mean, philosophically, I guess. 2 pi r is still 2 pi r even if no one is there to draw it.
Precisely. That is layer 1, the group SO3, the mathematical truth that things can rotate in 3 dimensions. Lillian argues this isn't a property of the atom. It's the rule the atom is born into.
That's trippy. So before the Big Bang, before the first particle, the idea of rotation was waiting there like a cookie cutter.
That's a perfect metaphor. The cookie cutter exists in the drawer, even if you never buy dough. That's unelectic invariance.
Okay, I can hang with that. The rule exists. That's layer 1. What is layer 2?
Layer 2 is the holoelectric field.
Holoelectric.
Think hollow as in whole or complete. This is the continuous, undifferentiated stuff of the universe, the coherence field. It hasn't been sliced or diced yet. It's just potential. It's the smooth fabric.
So sticking with the kitchen metaphor, this is the dough.
Exactly. Layer 1 is the cookie cutter, the rule. Layer 2 is the sheet of dough, the stuff.
Okay, I have a cutter, I have dough. I think I know what happens next.
You apply the rule to the stuff.
Yeah.
And that gives you layer 3, the relational layer. This is where spherical harmonics actually live.
So the spherical harmonic isn't the dough.
No.
And it isn't the cutter.
No. It is the result of the cutter pressing into the dough. It is the decomposition of the field under the constraint of symmetry. It is the specific shape that emerges when the potential is forced to obey the rule of rotation.
That actually makes total sense. It changes how I view those textbook diagrams. When I see that dumbbell shape of a orbital, I'm not seeing a particle that happens to look like a dumbbell. I'm seeing the field being forced into a specific relational mode because it has to respect rotational symmetry.
Correct. The paper puts it beautifully. It says spherical harmonics are symmetry-conditioned relational decompositions. They classify how different parts of the field relate to each other directionally. They organize the chaos.
This leads to a huge point in the paper regarding discreteness. Because quantum mechanics is famous for being discrete. Quantum literally means a chunk. Energy levels, particles, it's all pixelated. But the paper argues that this discreteness isn't primitive.
This is a profound insight. We often think of the universe as being made of Lego bricks, fundamentally discrete little atoms. But Lillian argues that the discreteness is spectral. It's derived.
Explain that distinction, derived versus primitive.
Think of a guitar string. The string itself is continuous, right? You can slide your finger up and down the neck. It's smooth.
Right.
But when you pluck it, you don't get a continuous sound. You get a note, a specific frequency. And if you put your finger on the 12th fret, you get the octave. You get harmonics.
Distinct notes.
Exactly. The notes are discrete, but the string isn't. The discreteness happens because the string is tied down at both ends. It's closed. The boundary conditions force the continuous string to vibrate in discrete steps.
So applying that to the atom,
The field, layer 2, is the continuous string. The symmetry, layer 1, is the anchoring. When you force the continuous field to close on itself under rotation, to wrap around a sphere, it can only vibrate in specific notes.
and those notes are the shells.
Those notes are the shells. The electron shells are just the standing waves of the universe playing the chord of SO3.
That recontextualizes everything. We aren't looking at a pixelated universe. We are looking at a resonant universe.
The resonant universe. I like that. And visually, if you look at the hydrogen wave functions discussed in the source, this split is completely visible. You have the radial part, how far out the electron goes, which is the energy dynamics. But the angular part, the shape, the spherical harmonic, that is pure relational symmetry. It doesn't care about the energy. It cares about the rotation.
So the shape is the symmetry and the size is the energy.
Broadly speaking, yes. And the paper argues that this relational layer is where the heavy lifting happens. It's where the machinery of symmetry actually operates.
Which brings us perfectly to section 2, the machinery of symmetry. Because if symmetry is the engine, we need to look under the hood. The paper has this fascinating, slightly dense section on what it calls the seed equation.
Ah, yes. The seed. Negative e to the I pi equals 1.
Euler's identity. The most beautiful equation in math. People get it tattooed on themselves. But the paper treats it almost like a functional component, like a gear.
It treats it as a special character evaluation. Let's unpack that. We usually see e to the I pi as just a number. But in this context, e to the I theta represents a rotation. It's the fundamental representation of U1 symmetry on a circle.
Okay, stop. A circle. U on 1, that's two-dimensional rotation, like a clock face.
Correct.
But we are talking about atoms, we are talking about spheres, three-dimensional objects.
Yeah.
So here is my problem. You can't build a 3D ball out of a 2D circle. If I spin a plate on a table, it doesn't become a ball, it just spins. So how does the seed of a circle create the sphere?
You would think it shouldn't work, right? This is where intuition fails us and group theory takes over. Lillian argues that the circle is embedded in the sphere.
Embedded how?
Think about a globe. Pick the North Pole and the South Pole. Now, draw a line of longitude.
Okay, I see the line connecting the poles.
Now, spin that line around the axis. What shape do you trace out?
I trace out the surface of the Earth, I trace out the sphere.
Exactly. The seed is that spinning action, that simple U1 rotation. When you embed it inside the larger 3D structure, which we call SU2, forces the math to expand. It's like the math has to invent the rest of the sphere just to accommodate that rotation physically.
So because you have the seed of rotation, the math grows the whole tree.
That is a fair way to put it. The symmetry groups are rigid. If you have the seed, the group structure implies the rest of the ladder. You can't just have the rotation. You have to have the structure that supports it. This leads to the creation of the angular momentum quantum number, L.
And this creates the ladder, L equals 0, 1, 2, 3.
Yes. The SPDF orbitals. They are the inevitable hierarchy of modes that allow the sphere to resonate.
And this is governed by an operator. The paper mentions a script A equals negative delta sub S squared, the angular Laplacian.
The Laplacian on the sphere. This is the closure operator.
Okay, Laplacian is another one of those words.
Think of the Laplacian as a vibration checker. It asks the field, are you smooth? Do you fit? It is the mathematical tool that enforces the symmetry. It says, if you want to exist on this sphere and respect this symmetry, you must vibrate at these specific frequencies.
And those frequencies correspond to the quantum numbers.
Exactly. But what is more physically tangible to us, and what I think you really want to know as a listener, is the degeneracy, the magic numbers.
Yes. Let's talk about degeneracy. In physics, that usually means different states with the exact same energy.
Correct. Imagine you have a conceptual bucket, the size of the bucket. How many distinct states fit into that energy level is determined by the symmetry. For rotational symmetry, the formula is 2L plus 1.
Okay, I want to run these numbers because the pattern is startlingly simple. If L is 0, that's the s orbital. 2 times 0 plus 1 is 1. One spherical ship.
Yeah.
If L is 1, the p orbital 2 times 1 plus 1 is 3. That's dumbbell pointing x, y, and z.
Correct.
If L is 2, the d orbital 2 times 2 plus 1 is 5.
And so on. 1, 3, 5, 7, 9. The odd integers. The paper emphasizes that this sequence is not accidental. It is the dimension of the irreducible representation of SO3.
That is a mouthful.
It means that if you have a perfectly round sphere, you cannot have, say, 2 states at a specific level, or 4. Geometry forbids it. The buckets must come in sizes of 1, 3, 5, and 7.
That is mind-blowing. It's like buying eggs, but the universe only sells cartons of 1, 3, 5, and 7. You simply cannot buy a six-pack of angular momentum states.
Not if the symmetry is unbroken, no. This is the theorem the paper highlights. Shell degeneracy jumps are determined solely by representation-theoretic multiplicities.
And the implication here is that I don't need to know what the atom is made of to know these numbers.
Exactly. It could be an atom held together by electricity.
Right.
It could be a planet held by gravity. It could be a nucleus held by the strong force.
Mm-hmm.
If it rotates and has spherical symmetry, the conceptual containers, the buckets will always have sizes 2L plus 1.
So the container shape is universal. But, and this is the big pivot to section 3, just because you have a container doesn't mean it's full.
Correct.
Just because the math says there is a bucket of size 5 here, does the atom actually use it? Because when I look at the periodic table, I don't see infinite orbitals. I see a very specific order. We fill the s, then the p. We don't just jump to the g orbital or the z orbital.
You've hit on the exact distinction Lillian makes in section 3.
Okay.
He distinguishes between sector decomposition, which is the buckets existing, and shell activation, which is the buckets being used.
Activation. That sounds active, like flipping a switch.
It is, and this is arguably the strongest contribution of the paper. Usually in physics class, we cheat a little bit.
We cheat. I knew it.
We do. We take the hydrogen equation, we solve it, and we say, look, the shell exists. Then we take the harmonic oscillator, solve it, and say, look, it exists there too. We treat them as separate miracles.
Right. It's like memorizing 2 completely different zip codes.
Exactly. Lillian stops and asks, is there a universal law, a single mathematical inequality that predicts when a shell turns on, regardless of what force is pulling on it.
So he's looking for the on switch for reality.
And he finds it. He calls it the variational activation criterion.
I'm looking at the equation here in the notes. It looks nasty. M sub L of A is less than negative C sub L times A to the power of, okay, walk me through this. No jargon. What are we looking at?
Think of it as a tug of war.
Okay, I'm visualizing a rope. Who's pulling?
On the left side, the M sub L, that's the nucleus.
Oh.
That's the attractive force. It's the come here force. It wants to pull the electron in tight.
Okay, gravity, electricity, whatever. The bowl.
Right. On the right side of the equation, that negative term with all the exponents correct, that is the cost.
The cost of what?
The cost of spinning.
Ugh.
Centrifugal force.
Exactly. Imagine you're on a merry-go-round. If you sit in the middle, it's easy. That's the s orbital. L equals 0. No spin cost. You can sit there all day.
But if I move to the edge...
If you move to the edge and the merry-go-round spins up to orbital speed, you feel a push. You have to hold on tighter.
And if I go to d orbital speed...
You're hanging on for dear life. That is what the right side of the equation represents. As the angular momentum, L, goes up, the cost of staying in the atom skyrockets. It grows exponentially.
So the equation is basically checking, is the nucleus strong enough to hold on to me while I spin this fast?
Precisely. And if the answer is no, if the inequality fails, the shell doesn't just sit there empty. It physically cannot manifest. It remains virtual. The bucket is there, mathematically, but the merry-go-round is spinning too fast for anyone to sit in it.
That creates a really interesting image. It means there are ghost shells all around us, mathematical possibilities that the universe creates, but the forces just aren't strong enough to populate. That's a beautiful way to put it. Ghost shells. And this leads to what Lillian calls the monotonicity rule.
Monotonicity, meaning one tone.
In math, it basically means preserving the order. Because the cost gets higher the faster you spin, you must fill the cheap seats first. You physically cannot have an atom that has an active f orbital, L equals 3, but a broken s orbital, L equals 0.
The merry-go-round rules are rigid. You fill the center, then the middle, then the edge.
And this explains the stability of matter. If you could activate high-spin shells at random, atoms would be chaotic. They'd fall apart. The cost barrier forces them to build from the ground up.
There's also this concept of the activation radius. A sub-L star is proportional to the square root of L.
This implies that higher angular momentum shells require a larger spatial region to manifest. You need more room to host a high-spin state. A tiny, tight box cannot support high angular momentum modes. They just get crushed by the barrier.
This connects the geometry of space to the geometry of the shell. Okay, so to recap, we have the theory, we have the buckets, 2L plus 1, which are universal, and we have the rule for filling them, the activation criterion. Now, I want to see this in the real world. Section 4, case studies.
We have two classic contenders, the Coulomb potential, like in hydrogen, and the harmonic oscillator.
Let's start with hydrogen. This is the one we all know. The electricity is pulling as 1 over R.
In the hydrogen atom, we observe that the energy drops as 1 over n squared. Now, if we look at the degeneracy, the total number of states in a shell, it is exactly n squared.
Wait, let me do the math here. N is the principal quantum number. So for shell, n equals 1, degeneracy is 1 squared. 1, just the 1s orbital.
Correct.
For n equals 2, degeneracy is 2 squared. 4, that's the 2s, which is 1 state, and the 2p, which is 3 states. 1 plus 3 is 4.
Yeah.
For n equals 3, degeneracy is 3 squared. 9. 3s is 1, 3p is 3, 3d is 5, 1 plus 3 plus 5 is 9.
The math holds perfectly. The paper calls this a perfect closed-form ladder. The sum of the odd numbers, 1 plus 3 plus 5 and so on, always equals a square number.
That is a beautiful piece of number theory hiding in the atom. The sum of the first n odd numbers is n squared. It's like the atom knows basic arithmetic.
It is elegant, and it shows that the hydrogen atom is a maximally degenerate system. The symmetry is so perfect that all these subshells, SPD, lock together into one big energy level. The math matches the periodic table structure perfectly.
Now compare that to case B, the harmonic oscillator.
This is more like a mass on a spring, or how protons and neutrons move inside a nucleus. The potential isn't 1 over R, it's R squared. It gets stronger as you pull away, like a rubber band.
Parabolic potential.
Right. Here, the degeneracy doesn't grow as n squared. It grows as n plus 1 times n plus 2 divided by 2.
That's a completely different formula.
It is. It grows quadratically, but with a different slope.
Oh,
However, and this is the key point, it is still built out of those two L plus 1 blocks.
So even though the total count is different, the bricks are exactly the same.
Exactly. The synthesis the paper drives at is that despite the different forces, Electrostatics versus nuclear binding both follow the rule. Counting functions jump in integer steps defined by the symmetry group. You're simply stacking the 1, 3, 5, 7 blocks in different arrangements.
So the bricks are universal. The architecture just depends on the force.
Beautifully put, and this universality is what allows us to play detective.
This leads us to section 5. The paper calls it symmetry rigidity, but I'm calling it the detective work.
It is an inverse problem. Usually in physics, we say, here's the shape of the drum, what sound does it make? Now we ask, here is the sound, what is the shape of the drum?
Can you hear the shape of a drum? That's a famous math paper, isn't it?
It is, by Mark Kanarek. And Lillian applies that logic here. He dives into Obata rigidity and the Lichnerovitz bound.
Lichnerovitz, now that is a name. It sounds like a wizard. I cast Lichnerovitz on you.
It is spectral geometry, which is close to wizardry. The core idea is this. If you measure the spectrum of an object, its vibrational frequencies, and you find that the first energy level has a degeneracy of exactly n+1, where n is the dimension, the object must be a perfectly round sphere.
Wait, so if I find a mystery object in space and its first vibrational mode has a degeneracy of 3 + 1, so 4.
It is a sphere. Not an egg, not a cube, a sphere. The math is rigid. The spectrum betrays the geometry.
You can tell if a sphere is perfectly round just by counting the degeneracy of its vibrations. You don't even have to look at it.
Yes, this is maximal degeneracy.
But what if it's not round? What if it's an egg? Or a squash sphere? Does the math break?
The symmetry breaks.
Yeah.
And this connects to the Zeeman effect.
Explain that.
Imagine our orbital bucket. It has size 5. If the system is a perfect sphere, all 5 states have the exact same energy. They sound the same note. They are in unison.
A pure chord.
But if you squash the sphere, say, apply a magnetic field, or physically deform it, that cluster of 5 splits apart. The bucket breaks.
So instead of one loud note, I hear 5 slightly different notes.
Correct. You get a dissonance. And the paper argues that this splitting pattern is a diagnostic tool. The way it splits tells you exactly how the symmetry was broken. Did you squash it into a pancake? Did you stretch it into a cigar? The frequency splitting maps perfectly to the geometric deformation.
So spectral splitting is like a forensic fingerprint of the crime scene. Who broke the symmetry? The spectrum knows.
The spectrum knows. And the paper goes even further with inverse spectral geometry. It suggests that if you see persistent clusters of eigenvalues, even if they are a little fuzzy, it implies there are closed geodesics in the system, stable orbits.
So the ghost of the symmetry still haunts the system, keeping things organized even when it's not perfect.
Precisely. The wave traces show where the symmetry used to be.
This feels like we are touching on something universal, but the paper takes one more giant step, up into the 4th dimension, section 6.
The 4D chiral bivector fields.
Okay, chiral bivector. That sounds intimidating. I'm still recovering from Lichnerovitz. Let's break it down. We are moving from 3D space to 4D space-time.
Roughly, yes.
Yeah.
Or just Euclidean 4D space.
Yeah.
The geometry changes. In 3D, rotation is simple. You spin around an axis. In 4D, things get double.
Double.
Yes. In 4D, the rotation group SO4 happens to decompose into 2 copies of the 3D rotation group. So 4 is isomorphic to SU2 cross SU2.
I can't visualize 4D. I've read Flatland. I've tried. Can't do it.
No one can, really, but think of it algebraically. A 4D rotation is like 2 3D spins happening at once, completely independent of each other.
2 spins.
And this creates a split in the fields known as the Hodge decomposition. You get 2 sectors, self-dual and anti-self-dual.
I've heard these terms in particle physics. Handedness. Chirality.
Exactly. Left-handed and right-handed fields. Think of your hands. They are mirror images, but you can't superimpose them. In 3D, we had 1 ladder of shells, SPDF. In 4D, because of this split, we get a double ladder.
2 ladders side by side.
Yes. A left-handed ladder and a right-handed ladder. And the magic numbers change. Instead of 2L plus 1, the formula becomes 3 times 2L plus 1 per branch.
So the buckets are 3 times bigger.
Yes, because of the extra internal degrees of freedom in the bivector field. But the pattern, the 2L plus 1 core, is still there. It's just multiplied.
Why does this matter? Why do we care about 4D bivectors? We live in 3D, well, 3D space plus time.
Because this is the language of relativistic fields.
Yeah.
Electromagnetism, gravity and spacetime, these are bivector theories. The paper is showing that this shell mechanism, the thing that makes atoms have layers, is also the thing that gives structure to the fabric of spacetime itself.
It universalizes the concept. It's not just for atoms. It's for reality.
It connects the shell concept to particle physics, spin, and chirality. It shows the mechanism is universal, not just for atoms. It implies that shells are not a quirk of matter, but a property of dimensions.
We've covered a huge amount of ground, from the Humboldt orbital to 4D chiral ladders. I want to zoom out to the Eureka scale mentioned in Section 7.
Ah, yes, the internal rating system.
The paper rates itself as aiming for ESR 9.0, structural consolidation. That sounds a bit arrogant. I give myself a 9 out of 10.
It does sound high.
Oh.
But in context, it is a fair assessment of the goal. The paper claims originality not in discovering spherical harmonics. Lagrange did that centuries ago, but in unifying them.
It's the Steve Jobs approach. I didn't invent the phone or the internet. I just put them in the same box and made it work.
Exactly. The author is saying, I didn't invent the math, but I am showing you that shell formation, degeneracy jumps, activation thresholds, and chiral splitting are all the exact same thing.
They are all just symptoms of symmetry closure.
Yes.
Let's recap the 4-layer ontology one last time, because I think that's the takeaway that sticks. And I want to make sure you, as the listener, have this right. We started with shapes of orbitals. That's layer 4, the derived layer, the measurement, the thing we see.
Correct.
We peeled it back to layer 3, the relational layer, the harmonics, the cutters that organize the field. Then layer 2, the Hall electric field, the dough, the continuous stuff.
Yes.
And finally, layer 1, omnilectic invariance, the symmetry itself, the abstract rule.
Symmetry is the engine. It converts the coherent potential, the dough, into structured reality, the cookies.
And the shells. The shells are just the stacks of cookies.
That is a very delicious way to put it. But yes, shells aren't accidents. They are the fingerprints of rotational symmetry acting on the quantum fabric.
So what does this leave us with? When I look at that diagram of the atom now, I don't see a solar system. I don't even really see balloons.
Good easy.
I see a resonance pattern. I see a drumhead vibrating. And the shells are just the places where the drumhead creates a standing wave. And the reason they are there is simply because the drum is round.
That is the essence of it. And I would leave you with one final provocative thought from the paper. The wave trace concept.
Lay it on me.
We talked about hearing the shape of the drum. The paper suggests that if you listen to the drum beat of the universe, the spectrum of energy levels, the clustering of the notes tells you the symmetry of the drum. If the clusters persist, if you hear those chords of degeneracy, it means the symmetry is real. It means rotational invariance isn't just an approximation we use to make the math easy. It is a fundamental structural truth of the space we live in.
So we're essentially listening to the symphony of symmetry.
And looking for the chords.
That is beautiful. Well, next time you see a diagram of an atom or you look at the layers of an onion, remember, it's not just a layer, it's a captured symmetry. It's a bucket of size 2L+1. Keep your symmetries closed and your sectors decomposed, everyone. Thanks for diving deep with us.